What's that? We're on? We're on now? I I don't have pants on. Yeah, you're right. They won't even notice. Um, hey folks, greetings from sunny Berkeley, California. I'm sorry to miss you all this time, but I hope you're having a great day full of interesting talks. And today I want to talk to you about libp2p and HTTP. So I want to use HTTP. I want to leverage our 30 years of experience with writing applications on top of HTTP. It's a familiar building block that has a lot of benefits. We've built a lot of infrastructure on top of HTTP that I would like to leverage. Things like caching that let me deliver content to users faster and cheaper, or things like layer 7 load balancers, which can load balance and route HTTP requests in a smart way. We've also built a lot of tools to help debug and understand our HTTP application. Things as ubiquitous as Chrome's network panel, which lets us see every request that goes through, how long it took, what it contained, and how the server responded. And here's my problem, I don't want to give up the benefits of a peer-to-peer system. If my application is valuable to at least 2 users in the world, it should still work, even after I'm done paying for a server. And speaking of servers, I don't want to rely on a central, well-connected server for uptime or discovery. If my server goes down, I want my users to not even notice. I want my application to be as resilient as the collection of peers using it. Those peers might be behind NATs or firewalls, and I want a whole bunch of those. So how can I get the benefits of HTTP and the benefits of libp2p? Before we go into that, let me introduce myself. I'm Marco. I've worked on libp2p for 3 years. I maintain Go libp2p, which itself is used as a building block for distributed applications like IPFS, Ethereum, and others. I quite like HTTP. It's impressive that it stayed roughly intact for almost 30 years. I think it's due to its simplicity and flexibility. So I was excited to try to bring it to libp2p. So when I say HTTP, and I think this is true when others say HTTP, I'm referring to HTTP semantics. Technically RFC 9110, which is basically the idea that I can send your request to a resource with attached metadata about the request, such as method and headers, and I receive a response with headers and the content. Contrast this with what I call HTTP encodings, like HTTP 1.1 or H2 or H3, which is about how to convert the HTTP semantics into bytes. And then contrast this again with like the underlying transport, which is how those bytes are transferred, like TCP or QUIC. Although in practice, these are really related, as H3 runs only on QUIC and HTTP 1.1 and H2 run on TCP. But the most important thing about the whole HTTP system, I'd argue, is the semantics. It's how we can agree on how middle boxes, load balancers, proxies, and caches should behave and handle our requests. It's how we provide actionable errors to users. And it's how we can support so many different applications. So I want to use HTTP semantics. So how do I do that using libp2p such that I can keep the benefits of a peer-to-peer system? And that's where the new libp2p HTTP spec comes in, which can be found in the libp2p specs repo on GitHub. In a nutshell, it encodes HTTP messages as HTTP 1.1 syntax and sends those bytes over a libp2p stream. This stream can run on any existing libp2p stream transport, such as web transport, WebRTC, QUIC, TCP, or WebSockets. And it's actually a funny idea of running this on top of web transport, as this means you're running HTTP over web transport, which is a stream on top of HTTP 3. Seems kind of pointless, right? Why do HTTP 1.1 over essentially H3? Why not H3 directly? It's a good question. You see, web transport has this nifty ability to be able to declare what you expect the server's public key to be. This means you can have a secure connection without having to rely on the server having a domain name and signed TLS certificate. It's very important in browsers. In practice, this simplifies deployment of peer-to-peer networks, since a peer just needs to be accessible. It doesn't need to plug into the web PKI infrastructure. So let me just take a little tangent here. While we're talking about the spec, let me point out that the spec also defines a well-known endpoint for nodes protocols. This is a resource that returns what protocols the node is running and where they can be found. For example, it can tell you that a node is running the ping protocol and it can be found at /ping. The idea of a well-known endpoint to describe a server isn't common in standard HTTP deployment, because it's usually the same entity that controls the client and the server, so both sides know where the resources are. But in a peer-to-peer network, each node may want to control what their resource layout looks like. Maybe you don't mind having your ping endpoint at /ping, but I'm also hosting my blog on my node, so I'd rather host my ping endpoint on /debug/ping. The well-known resource is how we learn what a peer supports and how it's configured. So I just told you how supporting HTTP semantics is just a matter of encoding messages per HTTP 1.1 and then sending them over a libp2p stream. Problem solved, right? Yeah, but I want this to feel like using a standard HTTP system with peer-to-peer superpowers. This means using standard HTTP types and APIs that are ergonomic in the host language. For Go, this means using the standard library HTTP types, and for JavaScript, this means using the fetch API request and response objects. HTTP semantics also make use of URIs as a primitive. For example, we can return a 301 response to redirect to a different URI. So we needed to find a way to be able to turn a multi-attr, which is libp2p's primitive for addressing nodes in a network, into a URI and back again. And we need a way to reference HTTP resources in a multi-attr. This will let us reference an HTTP resource using our multi-attr URI scheme. Again, very useful for redirects. The HTTP path is the multi-attr component that encodes a resource. And here's an example of what example.com/foobar looks like in the multi-attr form. I think showing off some examples is the best way to show off this API. And keep in mind that my goal is to make this look and feel like using standard HTTP. So if the demos look particularly banal, then I've done my job. Here, the server is listing on both a web transport and a standard HTTP transport. It can handle HTTP requests on either transport. There's only a handler, an HTTP handler, defined in a single place. And here's the example Go client. Note that it's just a standard HTTP.client, and the URI is a multi-attr URI. Here's a server, a HTTP handler that works both in Node.js and the browser. And here's the client version in JavaScript. And this is a pretty standard fetch call, but using a multi-attr URI instead of an HTTP one. Adine built a Caddy plugin that lets your Caddy server listen on the libp2p stream transport as well. With a couple lines of config, you're able to also listen on a libp2p stream transport. So shout out to Adine for doing that. It's very cool. All right, let's look at a service worker example. I think this is kind of compelling. So let's load that up. Okay. All right, here we have a service worker example. Service workers can intercept fetch requests from the browser. So we can use that to serve all the requests over a libp2p HTTP rather than a standard HTTP transport. This website loads a service worker, which will intercept future requests to my server where I'm running a Grafana dashboard and a Kuba node. Let's take a look at some metrics that I've exposed in Go libp2p and proxied through the libp2p and HTTP setup. You'll see that once I click the link, it sets the multi-attr URL in the hash. It was a little fast, but it looks something like, here, let's go back. It looks something like this, /pound multi-attr. That's just how this service worker setup handles it. So I go here and I can see my Grafana dashboard, can look at the resource manager. The resource manager dashboard is very useful if you feel like your application is getting stalled because of the resource manager blocking you. So if you see something here that looks bad, it should be pretty obvious. Another good dashboard to look at is the swarm. This is just the overall health statistics of your Go libp2p node. And if you're not familiar with this and you're running a node that uses Go libp2p, I highly recommend setting this up. It's very useful for debugging issues in production. And it looks really cool. Go to the Go libp2p repo and open the dashboards folder, and you'll find the README inside with more instructions. All right, let's look at another service worker example. On the same server, I have a git instance running, and I've exposed it through a libp2p stream transport. So we'll be able to access that here. And you'll notice that this as soon as the service worker starts intercepting requests, the URL looks as if we're just accessing the resource directly. So that's because the service worker is intercepting all the requests made by the browser. So this works as you expect. We can even read the raw stuff. We can even download the code directly. And let's look at the network tab. So let's make a request here. And we could see that we're going through the service worker. Let's open up. You can see kind of what you'd expect. You can see the request headers being passed. You can see the response headers, see the payload, the preview, and timing information. So all our usual tools work here. All right, now let's go back to the slides. Here's an example of a flood publishing style pub/sub application to distribute messages in a network. You can use this for a group chat or for sharing the latest block in the blockchain network. The API is pretty simple. We have a post request that informs the server about a new message ID we have, and we have a get request to fetch the message given the message ID. The way it works is that when a peer wants to publish a message, it makes a post request to let other peers know about its new message ID. The other peers will then make a get request to retrieve that message. Note that all peers act as both the HTTP server and the HTTP client. The application is built on HTTP semantics, so peers don't care if they're connected via libp2p stream or a standard HTTP connection. This means that servers confront themselves with a cache, and the rest of the network behaves the same. So did I solve my problem? Remember, I wanted to use HTTP while also keeping the benefits of a peer-to-peer system. Applications run on top of HTTP semantics. They are agnostic to whether they're running on a standard HTTP stack or HTTP over a libp2p stream. Peers that want to leverage a standard HTTP cache can simply run the application as you normally run an HTTP server. And of course, peers that need to hole punch or don't want to set up a standard HTTP server can still run the same HTTP protocols using libp2p stream transports. It's the same application code running in either environment. But you tell me. Ultimately, it's up to you all as developers to use this. And while I believe this will simplify peer-to-peer protocol development and deployment, it's up to you all to make it happen. Here are a couple threads I think would be interesting to explore if you're curious to play around with this. Braid HTTP tries to solve the state synchronization problem. Think CRDTs. They have a protocol that runs on top of HTTP. State synchronization is a common problem across peer-to-peer networks, so it'd be interesting to get this working on libp2p. Run an ActivityPub server so that you can host your own ActivityPub instance with minimal setup, no domain name or TLS cert required. Run your blog on top of libp2p and HTTP. This would let one publish content without having to set up a server. Host your blog from your laptop. Uptime not guaranteed. Build a web app RSS reader that can fetch content from multi-header URIs. This is a corollary to the blog idea. Run an S3 compatible file server. This should be an easy proof of concept for peer-to-peer file retrieval with a common API. Finally, I leave you with this thought. We have so many things now that run on HTTP. Has it become the new thin waste of the internet? Why not also do peer-to-peer with HTTP? Thanks for listening, and let me know what you build.